In this video, we are going to look at an example that is related to related rates. And so we're looking at a related rates example. So let's look at our example. A fish is reeled in at a rate of 1 foot per second from a point 10 feet above the water. At what rate is the angle of elevation theta between the line and the water changing when there is a total of 25 feet of line from the end of the rod to the water? Whew, there's a lot happening in this problem. So let's first draw a picture. All right, so we have a fish is reeled in at a rate of 1 foot per second from a point 10 feet above water. Right, so we have this person. This person has their fishing pole. This length right here is 10 feet above water. That value is not changing. So that value is not changing. We want to know at what rate is the angle of elevation between the line and the water. So the value theta, so this is our line right here. The water, the angle of elevation, that angle is theta. When there is 25 feet of line. So this length of line, we want to know what's happening when this length of line is 25. Is that length of line, is that changing? So as that person is reeling in at 1 feet per second, is that length changing? Absolutely it's changing. So we're going to give it a variable. We can't plug in that 25 yet. And so that's, we'll call the variable x. What does this value of 1 represent? Well, so it's being reeled in at the rate of 1 foot per second. So that is the change in length of line. So dx dt is equal to 1. Now, is that length of line, is it getting bigger? So is that increasing at 1 foot per second, or is it decreasing? It's decreasing. So that dx dt should actually be negative 1. Great. All right, now we need to come up with an equation that relates x and theta. So what is an equation that relates an angle to a side of a triangle? Oh, well, we have trig ratios, right? So sines, cosines, tangents. So we have, right now, we've identified this side. We also know this side of the triangle. So what is the trig function that relates the opposite side and the hypotenuse? Well, that trig function is sine. So sine of theta is equal to opposite 10 over hypotenuse. Great. So now we have this relationship between theta and x. Now we're going to go through and we are going to implicitly find our derivative. All right, so derivative of sine is cosine theta d theta dt is equal to negative 10 x to the negative 2 dx dt. So that is our derivative that we found implicitly. Now we need to plug in what we know. So what do we know? Well, we know dx dt is negative 1. We also want to know what's happening when x is 25. So if x is 25, then sine of theta is 10 over 25. So I'm going back to this relationship between the angle and the length of line. So theta is the inverse sine of 10 over 25, which is approximately 0.4115. And we have those values, and we are going to plug those in, plug those right into this down here. So we have cosine of 0.4115 times d theta dt, which we don't know, is equal to negative 10 over 25 squared times negative 1. And so d theta dt is equal to, if we go through and solve that, 0.0175. The units on this would be radians per second. That is our solution. Great. So that's how we could roll through that. One thing I might mention on this problem, one other thing, we could have done this without finding this value of theta. We could have drawn this triangle that's related to this specific situation. So when this is 25 and this is 10, we could have found this remaining side using the Pythagorean theorem. So this is theta. And so this side right here would be the square root of 25 squared minus 10 squared. And then your cosine of that is this side over this side. So we could have found that value of cosine without knowing the angle theta specifically. Although in this problem, we could find theta. All right. In our next video, we will look at another example where we are looking at some related rates. We will see you there.